Hello everyone. In this lecture 21, I show you how our earlier observation of non-quiescent stress relaxation from step shear could allow us to predict that delayed wall slip can also take place. After that, I'll move on to chapter 13, which focuses on a parallel set of phenomena regarding step extension, and showing you that localized elastic yielding also takes place. After a brief discussion about FSR, how it conducts a stress relaxation experiment, I will spend most of my time on updating the content of this chapter in terms of a new experiment where the localized yielding is observed in a confined case that is basically achieved through squeezing. All right, so let's move on and finish the rest of chapter 12. You can see this is so far a case of relying on, initially at least, relying on the movie showing non-quiescent relaxation to give us a sense that the sample, in absence of any further ongoing deformation, could break apart. This break apart does not have to necessarily generate microscopic motion. As I argued quite intensely that you can have a case where the breakup will occur homogeneously. So now let's borrow that insight that something magic happened upon shear scission. In other words, I want to indicate, maybe through this figure, I want to indicate that if you don't stop your shear, you start to see the sample break up well after the overshoot. Yet, if you stop shearing, the breakup could occur way before the overshoot. That's perplexing. No, so you do the same startup shear. If you're willing to do it as if it's a continuous shear, so you just watch with your movie, you'll find the sample could break up after the overshoot point, the shear bending, which is subject of chapter 9. Chapter 12 is a subject about terminating that startup shear even before the yield point. So you terminate it, for example, beyond the threshold, anywhere here, you find after termination, the sample would break up. Meaning, let's say it break up at the strand of 2. Whereas if you don't stop, you have to shear until it's strand of 5. So the termination of shear actually induced the failure to occur, quote unquote earlier, meaning it required less strands for the failure to occur. And it occurs in absence of any ongoing deformation. So it's absolutely peculiar and difficult to understand to begin with. As I mentioned last time, we of course eventually did figure out, I don't know where would they had it. We eventually, can't believe it. We eventually did figure out that, I don't see it anymore. Oh yeah, it's here. We eventually did figure out what it means. Remember, by the summer of 2006, we figured out the physics of it. The physics of it is, as I said, is somehow shear scission could induce earlier failure. In other words, using a language we are yet to describe, could induce force imbalance. I know this means nothing for you, but I just want to give you the sense that the same could happen when you encounter wall slip. In other words, if you have a problem where the sample will undergo wall slip here. If you recall, in the chapter 6, when we talk about wall slip, I emphasized most of work prior to our studies speak about wall slip in steady state sense. It does not answer the question of how wall slip come into being. In other words, how you generate from no wall slip and all of a sudden wall slip occurs beyond this point. By particle tracking velocimetry, we could visualize how it happens and answer the question that you require certain condition for wall slip to occur. So by the same token, if, just like the case of shear bending, which is something failure occurs internally, if wall slip is to occur here, can I anticipate slip to occur here if I stop shearing here? So it's the same physics as we did in the bulk. So we predict, this is the section 2.4, this so-called arrested wall slip. So I can predict that wall slip will take place earlier by me terminating here. Okay, so this is surely very strange. How can you? So here is the case, though. The movie was taken after we predict. Puyang was patient enough to make this experiment work. You have to make sure your surface is so clean. You have to have perfect absorption of your polymers so that you could delay your slip in a startup shear to this point. But he wants to demonstrate this can occur earlier if you stop. And this movie just shows it does. In other words, by the time he stopped the shear, no slip occurs yet. It occurs after you stop the shearing. We just call it arrested slip, but basically it's a delayed slip. So this is, of course, an amusing case where our insight about disentanglement in the bulk is something we learn from studying wall slip. And here's the case that we learn in reverse. By learning about what happens in the bulk, we start to predict further what could we learn about what happens at the surface. So this is a rather interesting example in that sense. Other than that, we're done with this subject in chapter 12. It's all about step strength. It's all about how termination of shear somehow made the failure possible to observe. Of course, just keep in mind, I can make an analogy actually. Studying wall slip versus studying failure in the bulk is almost like the difference between fracture mechanics and the conventional mechanics. The fracture mechanics introduce a cut. In your case here, the cut is your surface, is your wall. It has a bias. It allows you to prematurely fail when the bulk doesn't fail. And that's the same like having a cut in a sample to study fracture mechanics. So indeed, wall slip problem is a much simpler problem because you don't have to guess where it will fail in the bulk, which will be random, will not be predictable. Here we know where to look for. And in fact, precisely because of that, your particle tracking can be done by having camera on the top, just watching the surface. Of course, you'll still lose the information. This movie shows beautifully how the bulk is homogeneous being sheared. You don't get to see that if you have your camera on the top, as the arrow shows. But in fact, that was what was done by somebody else first. I mentioned in the book that there was some peculiar delayed slip that, of course, we have no clue why that could happen. In other words, why shear scission could induce slip. We'll get to that eventually when we come to chapter 16, when we discuss the theory. So with that, I think I'm covering
I have covered all the essence, basic parts of chapter 12. We spent quite a bit of time talking about it. And there are a bunch of data in this section that I'm going to omit it because you have the book, you can read what was done and nothing else to speak about. So I will just move on to chapter 13. And you may say, what is chapter 13? Well, let me remind you what our outline looked like. So we are in the middle of part 3. Chapter 12 is about step shear, and chapter 13 is about step extension. So it just completely, conceptually mirrors what we did in chapter 12. There, the story is the same, that if you understand the physics of this, what we start to call the elastic yielding, right? And if the yielding is inhomogeneous, is when you create motion. Sample break apart, that's why you have motion. Just like any elastic body, if you have a cut of the elastic body, the sample will snap back. So just like, so we learned that first from shear, and then we know the same physics must occur in extension. So all the results in chapter 13 are predictions in that sense. We predict things will happen if, instead of shear, simple shear, if we do uniaxial extension. So the idea, so I will go through some steps of this, and then update you with some work that was only completed after the book has been published. So let's go to this chapter 13. Okay, it's about step extension. So stepwise extension, if you want to be precise. And it's conceptually quite trivial to imagine. So basically you have a sample like this, and you're going to try to all of a sudden stretch like that and watch what happens. The beauty of this, just like what you did with startup, just as you did with startup extension, so this could be just an interrupted startup extension, right? Just like startup extension, you don't need pre-TV. You don't need any particle tracking, any tools. Everything is in front of you. Just extend and hold and watch what happens, right? And so this is where things gets a little bit where I should have copied a movie onto this lecture notes. But that also makes this lecture notes getting bigger and bigger in size. So I have no good way to save time and avoid crashes at the same time. So let me just be I think I have. No, there is no need for movie mode here. Let's see, where do I? Do I need to get rid of this pen again? I'm sure people are tired of me seeing me turning off this. And it does work. So I guess that's where, let me take a risk. That's where we need a play mode. This is what we did in shear. Remember, it takes 10 seconds for sample to break up. And then that motivated us to do extension. We also just do a step extension and predict, look, the shear is about to break up now. Yeah, start to break up. The shear start to break up. And predict that the same will occur in extension. Okay? As a prediction. because we understand the physics of shear is the same as the physics of extension. So that's really the zeroth order effect that that this chapter speaks about. And then the rest, I just want to highlight some of the rest of the issues, since I have already indicated for you the condition. So so this section, let's start with the first section. I kind of call it rupture-like failure after step extension, and it occurs under two conditions. So I will. In fact, I didn't even I don't even have movies, but they are in the literature. Basically, this after you step stranded, the failure appeared to be fairly sharp, so we call it rupture-like. There is a photo in the book. It appears fairly sharp, and that require a condition of not stretching very much. For example, by stretching by a factor of Weismann number equals, Hanke strand of 1, which is lambda 2.7, which is not a lot. You almost, but still significant. You triple your length almost and hold it. Then the failure will be like this. More importantly, we examine the condition again of very little stretching. So here the idea is again, if you don't stretch very much, the tube model will give you an impression nothing should fail because there's very little to retract from Rawls dynamics. So under this condition, we certainly find it's necessary to demonstrate even in this condition, sample fail. So that's what this section is. And the failure is relatively sharp. There's a bunch of speculations made in the book that I don't even need to go through. I'm just going by I'm just sort of quickly reviewing the phenomenology for you, okay? Yeah.
So you need to have both conditions active or just one at a time?
One at a time is fine. Either strands as little as just a Hanke strand of 1, or you use very low rate. In both cases, the deformation will tend to be the failure will tend to be fairly localized. We have some feel about why that is the case, but I'm not even developing that much here. The point being, it's actually, no matter what, indeed the sample was not very much heavily stretched. So the decohesion, the failure, or the force imbalance, whatever you meant to say about the failure, is really looking for fluctuation. They're really looking for a place that's weak, and then failure will occur there, instead of involving a larger spatial space of it. So I will try to, I'm very brief on this, and I will stay as brief as that. Okay, not much more. And then just on the second section, the condition where the rate is high and the strength is high, then usually the failure is a different type. So actually, let me just try to see I use that word here per se or not. I don't think I carefully use that word, but probably use it later. So you can casually just call this, if you like, decohesion. Whereas here, the failure apparently involves shear yielding. In other words, if you do it carefully, you'll find that if you stretch a piece of sample after step strand, let's say your sample look like this, then it turns out. So, let me just recall for you the convention. I know in the case of shear, man, after step shear, everything's supposed to be quiescent. All of a sudden you find it not quiescent. That sounds very striking. And since it's 1 millimeter, you never knew that would be the case. Extension should be less mysterious because you can just watch whether things moves or not. So supposedly should have been done many times prior to our experiment. Although I kind of claim this to be a prediction of ours, that after enough step strand, if you hold it, it will break. I'm sure industrial people who make tires have seen this many times, but probably they were never reported into the literature. What is known, apparently, is by Smith, is cross-linked rubber, if you wait long enough after step strand, can also fail. So people got confused about that feature with what we observed here. This is without cross-linking, and this is obviously something quite readily observable because you don't need anything, you just hold it. And hold it, our perception was no matter how much strand you use and hold it, this stretch sample should just relax quiescently, again, without breaking apart. And which means if you put any particles on the sample, it will just remain stationary. It should have. Of course, if sample is about to break, these particles, of course, will move. But actually, it turns out you can track those particles. You find the way they move. I know I didn't try to indicate to you. The way it moves is consistent with having shear type of failure, in the sense you may have this part moving much more than this part, and this part, like that. So this is not, I didn't discuss a lot more. Now I recall, even when we did startup, in the startup melt stretching, which also failed. Remember, in fact, I will come back so many times in the future. An untangled polymer melt, when you stretch with a high rate, you can never succeed in keeping this extension homogeneous until it flows. Instead, the sample breaks, and one of the dominant feature of breaking is shear. So there, I think I omitted it. It's discussed in the book. There you can, again, using a particle on the surface of your sample, watch how the particles is undergoing shear-like motion. Remember, this is you should be surprised by it in the following sense, because this is only extension. Don't you think the particle, if they move, should only move in a tensile way? Instead, in other words, there shouldn't be a variation across the sample thickness at any particular z position. But instead, it is different along this thickness direction, transverse direction. The particle does move differently. So by definition, it means shear. In other words, shear is a feature where its horizontal movement varies across the height. That's shear. So if you want to go into a little bit details, it actually, you can actually show that not only the particles on your sample is not motionless, but the motion of the particle is not tensor-like. It's instead shear-like, as I just draw it for you. Along the sample, transverse to the stretching direction, you basically spray your surface with some particle. The particle is just trying to report the motions of your sample. You find the motions of your sample is not uniform. It's not supposed to move. But once it moves, it's not moving uniformly. In other words, as I draw this, I think I draw it in a misleading way. I should have drawn it correctly for you. In other words, if I take a look at my particles here, I find some particles over time moved more, some particles over the same time moved less. So that's shear. I mean, that's right, across the transverse, yeah. So in fact, that's figure 13.6 shows that. So some particle moved a lot more than others at the same location. I know I'm using a coordinate here now, z. At the same z, for example, it moved differently. Okay, so I think that's there's nothing very much deeper I need to say, other than to say Mother Nature often find shear to be a convenient way of escaping, of undergoing failure. In other words, when the network is tight, stretched, it find, why not just at the angle start to fail like a shear? So that's the case. Since this, our work is supposed to be to make connections with what happens in the literature, and perhaps even be unbiased about what happens in the literature. I just want to indicate, I don't think I can afford not to indicate the case of how FSR treated stress relaxation in extension. So you probably have not heard me talk about FSR for a while now, 2 plates, and you have sample in between it, and you just extend it so that the sample become somewhat like this, right? Subsequent to some stretching. So this is your sample now, and they wish to do step strand experiment, which is to say that you extend by certain amount and you want to hold it. And the way they do it is by monitoring the very middle, again, of the dimensions of the sample in the middle. So, based on the physics we know, the sample will break. And it will, since you already have the middle being thinner than others, it will break from the middle. This, you can call it the end of rheology, because rheology is supposed to have all the strength field prescribed, either during or after. And this is out of control. Out of control is not conventional rheology. So we call it end of rheology. But this device is saving you from reaching the end of rheology. It's trying to say, let me be a little bit accommodating. If you want to break, I will move my crosshead backward so that it doesn't break. But I don't know anywhere in textbook this is still called stress relaxation experiment. You are moving everything intentionally. So, of course, I'm in very much disagreement with this way of reporting this as stress relaxation experiment. We understand why, the physics, because it's want to break, and you're trying to, oh, don't break, don't break. You move your boundary backward. So how can you have a stress relaxation experiment where you have a moving boundary? I see you laughing, but that's what happens. It's pretty weird. So, of course, if you want to report this manner, I actually reproduces their data that indeed you just have to move the crosshead backward. So this is, to me, very strange, and it's certainly, to me, doesn't look like a textbook definition of stress relaxation experiment. It has certain very peculiar protocol of maintaining that this middle part remain unchanged. So I just find that to be quite intriguing because I think if you read 2008, it is one of the papers that did this. And 2008 was also about the time, 2007, 2008, was also about the time we're saying the sample must break. Or we're observing the sample actually break. And they're saying, oh, I can save it from breaking. So there was a controversy and debate right at that point between our group and other groups. And I wouldn't say the rest is history, but I think this remains little discussed further, except these two groups are aware of these differences. I'm kind of rather uncomfortable saying anything further. I certainly don't know what else to say. I think I remember what I want to say. It happened at about the same time. But just imagine we never existed. We never had our motivation from shear that motivated us to do extension. Let's say we never existed. Would this just be the only thing in the literature then? This FSR way of doing stress relaxation. And would it be true that we would not be aware that if you do a textbook, I insist that what we did was a textbook step strand. Uniform sample, homogeneous extended, hold, and wait. Right? In fact, initially we were so careful that we worry so much about sample not being perfect that we actually extruded our SBR as a extrudate, circular extrudate. Watch this. As perfect as it can be, yet it still breaks. So that was the whole idea that could surface imperfection be the reason. In fact, subsequent theoretical or numerical work had a flavor that the failure occurs because of such instabilities, that you have a free surface. So there are studies, I doubt I'm going into it, but I can mention it very carefully, that there's a numerical study that took 6 known constitutive models, very simple ones. there are 6 models, and all of them predict that this will become unstable. I say this because I will introduce the next subject about getting rid of the free surface. Because you can indeed, if I don't know enough science, I can indeed just say, gee, maybe having the free surface was my problem, and it will break. So coming back to my topic, question, that we report a textbook step strand experiment will result of sufficient magnitude, will result in specimen failure. And it is elastic yielding, just like in shear. And we call it elastic breakup or elastic yielding. We are not trying to save rheology. We're trying to see what happens. If you want to save it, that part of the physics would be missing. You would never be able to observe it by definition. So I think I said enough. It's really up to the community to evaluate the differences. So let me turn to the last part that I intend to talk about today. I'm saying this is a part that updates the book because it's a part that was yet to be completed when the book was written. To me, this is a very crucial part of addition to the book or update to the book. And it has everything to do with what I just said. It has everything to do with getting rid of the free surface. So this is the last topic here that I had in the outline. The results were just published fairly recently. And if you read what I wrote there, it's kind of funny. I said there's probably is even incorrect, I may say. When you write something, sometimes you don't go through your brain enough times. So what I mean by absence of strand localization, right? What I meant by that was that the sample didn't fail. The dimension remained uniform. That's what I meant. Localized strand chain relaxation actually indeed produces localized strand localization. That's why this sentence is not quite correct. They are the same thing. What I should say is in absence of sample failure. So I want to carefully go through this because it really enhances or limits our options about what is the science here, about the nature of the failure that we are talking about here, the nature of it. In fact, with this new result that I'm about to talk about, I immediately send this new paper to the person who have used 6 models to show that this can happen. I asked, hey, can it still happen? Now I don't have a free surface. So let me describe this absence of free surface. So all along, relax, right? All along I knew that we want to do something. We want to do something about the squeezing device. All along. So this is why I had chapter 5, the last part of chapter 5 describing this particular geometry. So now I can simulate all these blank pages is no longer necessary. So, all right. So this is configuration I describe in, or draw a picture in a book in chapter 5 in the book. At that time, we knew this device would be very valuable in a couple of cases. One I already mentioned, which was to anticipate or to produce shear bending or shear strand localization in absence of free surface, in absence of any meniscus. Yes, you do have free surface, but they are irrelevant. They are the exit. They are trying to exit out. It has nothing to do with what will happen inside. And we showed in chapter 10 of this special case that you squeeze in absence of lubrication is dominantly shear, and that shear field can strand localize. In other words, can become unsmooth. A smooth deformation field will be parabolic. So we were, go back to that lecture, we were using laser, we were using a camera, we were watching how the sample could break apart or not. In fact, not enough work was done. It was very preliminary because that was a constant load experiment. It was not a constant squeeze state displacement experiment. And moreover, we didn't, in the no lubricated case, which gave dominant shear, we didn't do step strand. So that's one type. Here is the second one, why we built this device and why I want to describe it in the book, even though we had no results to report. A few results by the time of writing up the book. And that's this one. So we're going to envision, again, a trough with a piston here and loaded the sample between the piston and the lower base of that trough. Of that, basically a trench, if you like. Trough is fine, right? These words. Here we know from day one that you can produce a case of so-called planar extension. If you have lubrication. So this planar extension, don't be confused. In the literature, sometimes it's also known as pure shear. So in the dimension, in the way we have the XYZ dimension established this way, it is basically X is going to X0 stretched and Z becomes squeezed and Y does not change. The width doesn't change. So this feature, this scenario is known often as pure shear, but it's also just exactly planar extension. It's extended this way at the sacrifice of the thickness changing with the width held constant. Held constant because of the two side walls, right? So our sides are lubricated. So imagine, so this was our dream case that we dreamed during the initial extensional work in 2008 about, gee, can we extend our sample, meanwhile have an invisible wall protecting our sample from being exposed to anything else? In other words, preventing the sample from adopting different thickness or different cross-sectional dimension. Because if you have a free surface, then for a given length, I can always have one part thicker, one part thinner, in absence of any constraints. This prevents it. This is uniformly squeezing down. No matter what happens internally, my dimension will not change. Or will be uniform. Right? At every part, my dimension is W times H. Everywhere. But not only that, in other words, there's no, didn't I write that? There's no failure. there's no failure of the specimen, right? Not only that, we got rid of the free surface. So there are two things we try to accomplish. The rest is a little bit of just for you guys, if you really have this device, what can you anticipate? Well, you have a piece of melt, and you can try to treat that as a piece of rubber. And if it's a piece of rubber, we had a formula about how to calculate its Helmholtz free energy in terms of rubber elasticity theory. So this is described in chapter 1. And you can plug this three relationship in to find out how the free energy changes upon this squeeze. Everything is about shape change, so this squeeze apparently amounts to planar extension, right? So they are equivalent in that sense. So it turns out that you could trivially show that this will give you 1/2 nkt lambda square 1/lambda square. Okay? And then the rest is quite trivial. If you want to find out how much stress there is, well, you can find out how much force there is by differentiate A with respect to Z. Right? So do you know how to do that? I mean, that's how you did it for rubber elasticity and lambda over Z. Okay? So it turns out when you have true stress, true pressure, which is F divided by, whatever. So you see, you have a transducer, so you can measure how much force, and this area is always fixed as A0. So you have, in that limit, you could find your true stress. Okay? And you find that true stress is G lambda squared 1/lambda. Okay? And so that's for compression. So if you do it in the compression sense. You can also try to, you're free when you do rubber elasticity. You can also try to do, evaluate the extensional force. In other words, you can differentiate, instead of Z, you can ask what is F. Right? You can. Okay, and that's just over lambda and then lambda over X. Okay? There, you find it quite interestingly. If it's true stress, you find the result is the same. Okay? So for this part, I'm glad you are here to keep me company. This part, you have to recall the extensional part. Remember, to learn anything about extension is to use engineering stress, not true stress. So it turns out the variable you want to use is not that, because that's true stress, is that divided by lambda. Okay? So it turns out that that's how you should think about it, and we're trying to relate that to the density of strands in the cross section, as well as the force involved, retractive force involved due to the change in lambda. So I found it by preparing the notes today that it was quite amusing that this force is of the form of 1/lambda, a third power there. In other words, if you calculate the force, They are all of the form of lambda 1 over lambda third power. The other functional form, like this, comes when you try to reconstruct the stress, which has to do with what area you are dividing. So it's only there you can get confused about what is the final result. So it turns out for us, the right way to think about, we know from day one, was engineering stress. So let me say something very slowly. In this device of squeeze, we have no way of measuring the stress. We have no way of measuring the corresponding extensional stress. We can only measure this tensile, this pressure. And therefore, based on the rubber elasticity, staring at this, we only have this formula. Gee, please, it's so slow sometimes. We only have this formula. But this is not quite the formula we want to use. This is the true stress. Why? We know it's true stress in the extensional case. When you imagine the stress in this direction. So this perhaps was a little bit of a struggle. So you eventually decide, I shouldn't report just the pressure. I should report the pressure the pressure normal after correcting the fact that there is a so let me be a little bit slow here. So what I'm trying to arrive at is a way to determine when I squeeze, when do I see my structure due to entanglement start to fail? The yielding, the signature of yielding. We learned from uniaxial extension, the signature of yielding is a non-monotonic peak in the engineering stress, the tensile force. And through this, we know that tensile force requires you to divide that true stress by lambda to get to the engineering stress. And therefore, we should do the same for this. Okay, that was the story. So we actually report the engineering stress, which is the pressure divided by lambda. And indeed, that shows a peak. And presumably, as an indication of too much shape change is causing, I now start to keep using this word, force imbalance. It's causing the disentanglement. It's causing the yielding to take place. So I think I said enough about this point. The rest of it is really a little bit of technicality with regard to how we want to proceed. So, okay, here you go. You squeeze by a factor of almost 4, for example. Quite a bit, right? You squeeze. What are you trying to learn? What we were hoping to examine such a scenario where you have no free surface, where you terminate your deformation after a large amount of strain. See, it's just after a large amount of strain, and you're going to watch what happens during so-called stress relaxation. Keep in mind, during this stress relaxation, the sample will be incapable of becoming globally unstable, because the geometry constrained it will remain rectangular no matter what. Nothing can happen. But we perceive inside this sample, this network could still break apart locally, in a localized manner. partially, at least partially, these two ends are still unconstrained, are free. So that was the starting point. We were examining a case where can we have the equivalence? Basically, it's this. Can we have the equivalence of what we observed here? Of course, this is not happening because this involves the dimensional change. There's no dimensional change. Yet, can something like this happen? That was the motivation. It's pretty crazy, right? And because we understand the reason this occurred is localized disentanglement, right? You got a network that's highly strained. If some parts start to, what's the right word? If some part start to weaken, then you see, in an experiment like this, if this part starts to weaken, your stress could rapidly drop because it has the ability to snap back, right? To lose the stress. There, of course, you don't have that. There's no way the sample fails, so the stress cannot really, straightforwardly speaking, you cannot see them. But here's the data. It looks like during the stress relaxation, you could still have a, geez. Nobody tells me the pen would be in what mode. So you could still have a kink-like feature. In other words, there is a sense that at some point, the relaxation was slightly faster, if you like. And if you make, I don't know what you call this. I don't know what you call this. This is probably, you can call it, in fact, there are two kinks, if you like. Right? Because there's a fast drop and then there's another fast drop. But keep in mind, of course, this fast drop has to do with the fact that you are on a log scale. But let's get to the reality. The reality is Ru Chao was able to report that if you squeeze by a factor of 4, you find during the relaxation, the sample will break apart, actually, even. But I think the simpler case, let me not focus on this one, is the following. So if you squeeze, and then you hold it for a while, anticipating there could be some disentanglement non-uniformly taking place. And then you unload. In other words, you lift your piston. If nothing happens, your sample should be smooth and homogeneous and bounce back, if not. But it turns out it's bumpy, and we call it wrinkles. It's bumpy. It's suggestive that even though it appears to be a single piece, inside something is happening in a inhomogeneous manner. And the only way to observe it is by lifting your piston so that you will find the residual stress in different parts are different. That's why the re-swelling, quote, or recoil back is not uniform everywhere. So it gives you wrinkles. And just to test that's the scenario, you can have your sample cross-linked to prevent that failure. And the sample is smooth in that case. Okay? So that part is quite, again, when I talk to people in the tire industry, they have seen that all the time. But we predict that without seeing it. It's like we were just looking for it and we know such thing must exist. there's a paper, right? So, look like that's the part I failed to do. So this is this is just for the recordings. This is a Journal of Rheology 2020 paper by Ruchao. So there are lots of details. I should mention just one or two more details. The very same experiment that give you wrinkles, okay? You will have, in two cases, wrinkle-free after a large step squeeze. One, if you squeeze by a factor of 4, but don't wait, immediately lift. It's smooth. It has no chance to undergo any failure and disentanglement and non-uniform relaxation, whatever. Second, what is the second one? It will still be uniform, wrinkle-free. The same experiment. One is limited lifting, one is wait a little bit and you see wrinkles. And lastly, what about you waited forever and then lift? Huh? Would that be smooth? It will have, if you give infinite amount of chain diffusion, everything eventually will be uniformly relaxed. In other words, even if you have the wrinkle, which did happen at 100 seconds, let's say that's a fraction of tau, but if you gave 20 taus, all these different cases will swim back into a case where every chain is homogeneous. And when you lift that, of course, it's going to be a simple sample. Right? So these are just sort of controls showing that there is this wrinkle that is peculiar. So we have demonstrated a case where the physics of the horse race occurs. You cannot be in control of that. They will occur. They will take place even though you have constrained it. You have prevented from any shape change along the sample. It can still occur. So lastly, a little innovation was really to do birefringence. Because it enables you to visualize this issue without lifting the piston. In other words, it would be nice to see just exactly how they are breaking apart without, because if you lift, you can only see the bump start to occur, right? The wrinkles start to occur. So the way to do that is really you have that squeeze device. And if you make that squeeze device, the bottom of that squeeze device transparent, and then you sandwich two cross polarizers, sandwiching between the sample. And the top piston, of course, also need to be transparent. Then you may be able to see something. In other words, under cross polarizer sandwiching the isotropic sample, of course, no light comes through. Okay. But the sample he's dealing with is what? 10 millimeters thick to begin with. Very thick. So if there's any birefringence, you quickly build plenty of birefringence. And therefore, we have to add a retardation plates made of melt-stretched polystyrene. So we know how much birefringence it already has. But the basic point is this, that again, I didn't steal it. I consulted them. They said I can reproduce this from the literature. But I did reproduce this Michael Levy chart from the literature into my book. I just find this is just a very clever way to look at any chain deformation that is spatially inhomogeneous. So here's this chart. It basically tells you if you have a white light which has all the different wavelengths. the rainbow colors, right? The white light has all the rainbow colors. Then, of course, according to the discussion in my book in chapter 3, if it's a single color, then the light will go through or not, depending on the so-called sign squared of the retardance delta. So your light may go through minimum and maximum over different amount of retardance. But that's for one wavelength. If you have different wavelengths, which is white light, then these humps tend to be like these humps that you see here. So obviously, when you have no birefringence, everything is dark, meaning this white light will not transmit through. And then as you have birefringence, you start to rotate one of the director's electric field of the light, and you start to have light coming through. And this colors just measures how much retardation there is. And the trick is, if I show you a retardance of blue, you don't necessarily know it's this blue or this blue. Okay? So that's the problem. Well, that's the problem with monochromatic light too, meaning you wouldn't know you are here or here. So to know that, it means you have to keep track of it. So as I mentioned before, that if you have a lot of birefringence, you tend to be in this saturated region. There's no information about the variations. Remember, this is a beautiful technique if you have spatial variations, because there will be a color distribution allowing you to claim that you have seen birefringence of different levels spatially across a certain region. So since we are going to produce a lot of birefringence, that quickly you would reach a saturated region. What we did was to use a retardation place to push our sample to have this birefringence before any squeezing. And in a negative way, so that upon squeezing, your retardation will go this way. So that was what that movie, that apparatus did. And you can be fairly quantitative by reading the colors if you can keep track of their history. And so this is just the details in the details in the paper about how you prove that there is a stress optical law more or less holds. And these are the two movies. I know we're running out of time. Basically, this is a slow movie just showing different color schemes at different times. So basically, we start from A because we had the retardation plate. And we see them traveling backward and reaching the end. And then they can, any further increase will move forward again. So we have the cycle of it. And the whole idea was, so this was an experiment where we can keep track and see where the birefringence go. So I know I'm running out of time, so let me just go to the last part. Same thing, you can use different rates. And you can, this involves 3 different rates. I'm not going through all of them. We label them as A or B or C. So all starting from this point. A1 is all here. A1, B1, C1 all start here because you have retardation plate. And then they go backward. And then eventually go forward again by reaching. And eventually, even this technique was not enough to deal with all the birefringence because eventually saturate again. So we only observe a small window, just like this one. We only observe the first part of when you switch, we only observe the first part of it. This is all saturated, this part. We couldn't observe it. So, but the objective is accomplished, which is this, that you make a big a large amount of squeeze, you watch the birefringence build up, and this is the best we can do. And you can see, yes, I didn't stop quick enough. See that black part, right? This part, that's traveling to the end already at that point. It already traveled to the end there. And then the subsequent beyond that point is moving forward again. Because the cancellation has finished. Because I put a negative retardation first. So any positive retardation is trying to cancel until cancel to 0, and then it moves forward again. So in fact, this movie actually finishes at about 40 seconds. So watch it. It's right now 18 seconds. So it's still squeezing. And you can see eventually saturated. We cannot see very well anymore. It's all saturated here. Spatially. So you cannot resolve much spatially. And the relaxation started around 40 seconds, right here. Okay? Look at the chaotic colors. Look at them. Very, very bad. So, in fact, this particular one shows that at some point the sample actually internally break. You see, this part is already broken here. This is not the sample. The sample already slided away. Yeah. So basically, it's very, very bad thing can happen. It breaks apart. Yeah. Look at how. And it breaks apart despite the fact you have a constraint. That's because these two ends are free to go. Yeah, it's playing, so you can see it's very unevenly relaxing. So I think this was just a interesting update on the idea that large amount of step strand is bound to produce force imbalance that produce disentanglement, and the disentanglement is a horse race, and they allow, yeah, so it allows different part to relax different amount as a result of this. And with that, I think we are done with chapter 13. We'll next time move on to move further now. Okay, let me just turn off here now.